I want to remind you of another concept called the current, probability current. Probability current. What is it? It's a J of x and t that, as you will review in the homework, is given by h over m, the imaginary part of psi star d psi dx. So it's a real quantity, and it's called the probability current, and it goes together with this probability density. Is probability density that we wrote over here. So it's the current associated to that density. Let's think a second what this means. In electromagnetism, you have currents and charge density. So in E&M, you have a current that is a vector and a charge density. Now, this current could also be a vector if you're working in more than one dimension. It would be a vector. But if you have electromagnetism, the most famous thing associated to electromagnetism currents and charge densities is the so-called conservation law. This differential equation satisfied by the current and the density. Divergence of J plus d rho dt is equal to 0. That means charge conservation. You may or may not remember that. If you don't, it's a good time to review it in E&M and check on that, discuss it in recitation, think about it. This means charge conservation as we usually understand it. And the way to do it, I'm saying just in words, is you think of a volume, you consider how much charge is inside, and you see that the rate of change of the charge is proportional to the current that is escaping the volume, which is to say charge is never destroyed or created. It can escape a volume because the charges are moving, but if it doesn't escape, well, the charge remains the same. So this is charge conservation, and this is the same thing. So the divergence of J in this case reduces to dJ dx plus d rho dt equals 0. It has a very similar interpretation. So perhaps in equations, it's easier to think of the interpretation. Consider the real line and a point A and B with A less than B, and define the probability PAB of t of finding the particle in this interval between A and B at any time. You should be able to show, and it's, again, another thing to review. This you can review. And this review as well. You will use this differential equation and things like that to show that dPAB dt, the rate at which the probability that you find the particle in this interval changes depends on what the current is doing here and what the current is doing here. So it's actually given by J of A and T minus J of B at time t. You can show. And please try to show it. So what does that mean? You can have the particle here at any time, but if you want to know how that probability is changing, you must see how it's leaking from A or how it's leaking from B. Now, J's are defined by convention positive to the right. So if there's a current, a bit of current at A, it increases the probability. This particle is sort of moving into the interval. And here, at B, if there's a positive current, it decreases the probability. So finally, for wave functions, the last thing we say is that these wave functions are, you want them normalized, but we can work with them, and they're physically equivalent if they differ just by a constant. So a psi1 and a psi2 are said to be equivalent if psi1 of x and t is equal to some complex constant times psi2 of x and t. Now you would say, well, I don't like that. I like normalized wave functions, and you could have a point there. But even if these are normalized, the two wave functions could differ by a phase. And they would still be physically equivalent. This is part of the definition of the theory. The definition of the theory is that these wave functions are really physically equivalent and indistinguishable. And that puts a constraint on the way we define observables. Any observable should have this property, that whether we use this wave function or the other, they are, give you the same observables. So if your wave functions are normalized, this can be a complex constant of length 1. Then one normalized implies the other is normalized. If they're not normalized, you can say, look, the only reason I'm not normalizing it because I don't gain all that much by normalizing it. In fact, I can do almost everything without normalizing the wave function, so why should I bother? And we'll explain that also as well very soon. So this is something that is part of the physical interpretation, and we should keep it.